नमस्ते दोस्तों, स्मार्ट माइंड्स ट्यूटोरियल्स में आपका स्वागत है। आइए आज कुछ नया सीखें।
So let us cover some important questions from Unit 2, that is permutation, groups and isomorphism. So the most important question is Lagrange's theorem on groups. So first let's see what is the statement. If G is a finite group and H is a subgroup of G, then we can say that mod H divides mod G. Here mod means order. Order of H divides order of G. Okay, so let us see how to prove this. Let G be a finite group. And H be the subgroup of G. Let the order of G and H be N and M respectively. That means order of G is N and order of H is M. So let us write that order of G is equal to N and order of H is equal to M. Let A1H, A2H, so on up to AKH be distinct left cosets of H in G. Then for A belongs to G, AH is equal to AIH for some I. And from properties of cosets, what do we have? A belongs to AH. Therefore, each member of G belongs to one of the cosets AIH. That is A1H union A2H union so on up to union AKH is equal to G. Now applying modulus on both sides. So what do you get? Mod A1H union A2H union so on up to union AKH is equal to mod G. Now we can separate the mods. So mod A1H plus whenever you have union inside the mod and if you are separating it, you get a plus sign. Plus A2H plus so on up to AKH is equal to mod G. This is equation number 1. From the properties of cosets, mod AH is equal to mod H equals to M for each A belongs to G. Now substituting the corresponding values. Substituting the corresponding values in equation number 1. So you will get M plus so on up to M. We will get K times. That is equal to N, which implies Mk is equal to N. which implies k is equal to n by m, which is an integer. Equation number 2. Now it can be seen from equation number 2 that m divides n. Therefore, you can say that order of h divides order of g. Hence proved. Take the next question. This is also very important. Prove that a group of prime order is cyclic. And for proving this, we will use Lagrange's theorem. So first, let us see what is the statement of this. If H is a subgroup of a finite group G, then the order of H divides the order of G. That is, mod H divides mod G. Here mod represents order. Let's start the proof. Let G be the group and prime number P is the order of the group. That is, mod G is equal to P. Since P is greater than 1, thus there is an element A belongs to G such that A not equal to E. The cyclic subgroup we denote by this generated by A is a subgroup of G. And it has at least 2 elements, A and E. Same as the prime number. A prime number, how it has 2 factors, 1 and itself. The same way here also, if it is of prime order, then it will have 2 elements, that is A and E. Now we use Lagrange's theorem here. According to Lagrange's theorem, the order of cyclic subgroup A, that is, order of cyclic subgroup A divides the prime P. Let's say order of cyclic subgroup A is equal to Q. But P is a prime number. Therefore, Q is equal to 1 or Q is equal to P. Why? Since 1 and P are the only divisors. Divisors means factors of P. A prime number has only 2 factors, 1 and itself. Now, since A not equal to E, modulus of cyclic subgroup A is not equal to 1. So, modulus of cyclic subgroup A is greater than 1. That means modulus of cyclic subgroup A is equal to P, which implies cyclic subgroup A is equal to mod G. So cyclic subgroup A is equal to G, which implies it is cyclic group and G is a group of prime order. Therefore, every group of prime order is cyclic. Hence proved. Now take the next question. This is also very important. Cayley's theorem. We need to state and prove Cayley's theorem. So to prove Cayley's theorem, first you should know what is meant by group isomorphism. So first let us see what is group isomorphism. So an isomorphism phi from a group G to a group G bar is a 1-1 and onto mapping from G to G bar that preserves the group operations. Phi of AB is equal to phi of A into phi of B for all A comma B belongs to G. Now let's see what is the statement of Cayley's theorem. Every finite group G is isomorphic to a permutation group. Now let us see how to prove this. Let G be a finite group. If A belongs to G, then for every X belongs to G, there exists a product AX belongs to G. Now let us consider a function FA maps G to G defined as FA of X is equal to AX for all X belongs to G. Now first we need to prove that FA is 1-1. How to prove it is 1-1? X comma Y belongs to G. That implies FA of X is equal to FA of Y. That means AX is equal to AY. A get cancelled, you will get X is equal to Y. Therefore, we can say FA is 1-1. This is the first property. Next, we should show that FA is onto. How do we prove that it is onto? If X belongs to G, then there exists A inverse X belongs to G such that FA of A inverse X is equal to A into A inverse X. So that is A inverse we will put together and we'll take this X outside. And we know that A into A inverse is E. E is identity element. E is same as 1. So 1 into X is X. That means FA of A inverse X is equal to X. Therefore, FA is onto. Now, as FA is 1, 1 and onto, you can say FA is a permutation. FA is a permutation on G. Let G dash is equal to FA such that A belongs to G. Now to prove G dash is a group with respect to product of two functions. So for this, first we will show the closure property. How to show closure? A comma B belongs to G. Let FA comma FB belongs to G dash. That means FA FB into X is equal to FA into FB of X. That is FA into, what is FB of X? It is same as BX. And FA is same as A into BX. That is AB into X, which is equal to FAB into X. So what did you get? Therefore, FAFB is equal to FAB for all X belongs to G. Now FAB belongs to G dash. Since AB belongs to G, therefore G dash is closed under multiplication. So this is closure property. Now we need to show associativity. For associativity, you need three elements A, B, C belongs to G. Let FA, FB, FC belongs to G dash. That means FA into FBFC is equal to FA into FBC. That is FA into BC. That is equal to FAB into C. That is equal to FA into FB. Outside we can write FC. Therefore, you can say FA into FBFC is equal to FAFB into FC. Therefore, G dash is associative. Next property, existence of identity. How do you show existence of identity? What is the identity element? The identity element E belongs to G. That means FE belongs to G dash. Therefore, FEFA is equal to FEA. This we can write FAFE is equal to FAE, which is equal to FA because E is the identity element. Therefore, FE is the identity element in G dash. Next, we need to show existence of inverse. How do we prove this? as A belongs to G, which implies A inverse belongs to G. Therefore, F A inverse into FA is equal to F A inverse A is equal to FE. So F A inverse is equal to F A inverse is equal to FE. Therefore, F A inverse is the inverse of FA in G. Therefore, you can say G dash is a group. Now consider a function phi maps G to G dash defined as phi of A is equal to FA for all A belongs to G. Now we prove that phi is 1, 1. To show that it is isomorphism, we should show that phi is 1, 1, phi is onto, phi is homomorphism. These three things we should prove to show that phi is an isomorphism. So first let us take phi is 1, 1. Now A comma B belongs to G. That means phi of A is equal to phi of B. That means FA is equal to FB. That implies FA of X is equal to FB of X. That implies AX is equal to BX, which implies A is equal to B. Therefore, phi is 1, 1. Now we will show that phi is onto. So FA belongs to G dash. For A belongs to G, F of A is equal to FA. Therefore, phi is onto. Now we need to show that phi is a homomorphism. Now if A comma B belongs to G, which implies A belongs to G, B belongs to G, which implies AB belongs to G. Then phi of AB is equal to FAB. That is equal to FAFB, which is equal to phi of A, phi of B. Therefore, phi is homomorphism. Now you have proved all the three. Now final conclusion. Since phi is 1, 1, onto and homomorphism, you can say phi is an isomorphism from G to G dash. Therefore, G is isomorphic to G dash. Okay.